So yes, I'm just more or less continuing to another technique that is not destructive and permit to make composition analysis on different samples. No. That is going, but not. Yeah, this too. Okay. Yeah. Yes, perfect. So, okay, this work is just in the framework of the Melody project that was already in part presented yesterday by Francesca Zambon for what regard the remote sensing analysis. Here is the, we can say, the work package that is related to the lunar meteorite analysis. We are working both studying petrography, mineral chemistry, and geochemistry, and the reflectance spectroscopy of those samples. No, sorry. So just to give a large introduction. So the reflectance spectroscopy is one of the main techniques that you can use to have clear information for remote sensing data of the mineralogy. Generally is the one that permits to have the better spatial resolution and the larger spectral resolution with respect to all the techniques. And so we have clearly indication related to the composition of the moon, the variegation of the composition of the moon already from multispectral sensor like Clementine cameras, but even more with the more recent spectrometry. I've just reported some information from M-Cube dataset, and you can clearly see the differences in composition using specific spectral parameters. And you can clearly see the variegation of the mafic mineralogy, the different relationship between pyrox and plagioclase in some region, the presence of clear indication of the plagioclase in specific points on the lunar islands in particular, and even some other mineral that has been detected, like some spinners from remote sensing analysis. So to work on these techniques in terrestrial laboratories permit to have a higher control on the sample and to correlate the data and to use them for make calibration of the remote sensing data. Often the work to permit to correlate information with the moon has been done considering terrestrial analogs like mineral mixture and so on of plagioclase, pyrox, and olivine, etc. Some works, obviously, in the beginning, particularly with the Clementine mission, was done using lunar sample return. Less work has been done considering the meteorites. Here is one of the few related to Erie et al. That work on the Antarctic meteorites from the moon. That is mainly important because they have less alteration, but they permit to indicate different phases, recognize plagioclase, different relationship between pyrox and plagioclase, and evidence using different parameters related to the absorption, how we can correlate the composition. And so this can be in some way directly translated then from the remote sensing interpretation. So what I didn't find at all in the literature is use the same technique with some images in the lab. So in this project, we are using two different hyperspectral camera that permit to go to 400 nanometer to 2500 nanometer. They are here at the Geoscience department of UniPd, and we're working with different type of meteorites. So there is a series of different breccias with variable characteristics. One more is coming. Then we have a troctolite and a basalt. Those are the image of the picture. Those are the images taken with the VNIR cameras, so RGB with these three different channels. And you can clearly see that they looks like as the sample impressed by a camera. So, and moreover, here you can clearly see that those samples are very interesting because give a larger variation of the information of the different clusters. Those looks like already at this scale more homogeneous, obviously. And this is the SWIR information. They are slightly darker because the spectral constant is lower, but we will see later the spectral information is higher. So they are particularly important. And this is a variation of the spectral characteristics that we can clearly see. So from the small portion of the breccias, we clearly evidence the presence of plagioclase. There is still some alteration, mainly related to the plagioclase, since this band is closer to the ILOH absorptions. Then a clear variegation of different pyrox and, or we say pyrox and plagioclase combinations. So sample that probably goes from neuritic composition with different amount of pyroxene and plagioclase. Some dark class that has a larger bands, probably attributable to some olivine in this class, and then the dark veins, that is the matrix that is characterizing the sample that is very dark. The troctolite, I would say, is much more homogeneous. The main rocks, and we'll see later, are characterized by the pyroxene absorptions. There is some clear evidence of olivine in some class and a peculiar millimetric scale ilmenite class. The basalt is more darker in general. There is less variegation, so the sample, we can say, is just characterized by this type of absorption. There is some class that is a little bit higher alterated, and so they are slightly brighter and they have much more, we can say, content of clay minerals, and some darker class that looks like similar, even with some larger absorption. It probably is characterized, but has to be confirmed by an higher oxide content, so probably magnetite, but we'll confirm with the petrographic characterization. And then we use this data set to start to make some classification. Since we are working for now with the two cameras separately, so we have not combined the data set. Here you see the image from the VNIR and the SWIR. We take some region of interest from the visible to near infrared, and we reclassify using this end member the samples. We can clearly see that more or less we can characterize all the samples. So for instance, this Chan region of interest characterize this region as well as this class, as well as some smaller class here, and so on. What is interesting from this side is that the area related to the vein was not able to be mapped in the sample. That is quite peculiar, but it's probably related with the dark and this, so the relative signal to noise ratio that is lower. Whereas when we consider the infrared, where the signal to noise ratio is better, we are also characterize that, and you see that the two spectral range, and we are mapping, even if with a different spatial resolution, the same cluster. So the two, anyway, the two different spectral range are permitting to characterize the same things. We can even reduce the angle of tolerance from the spectral angle mapper that was the classificator that I used. And clearly we can see that the main mineralogical characteristic remains. We lose a little bit the information that are in between the matrix and some cluster, or between some different plagioclase pyroxene classes. So technically, if we want to have a higher detailed information, we should find more end member that are in between the plagioclase pyroxene composition. So perfect. So another case from the troctolite, as you can clearly see, working just in the SWIR region, that the sample is mainly homogeneous, and if we consider those end member, we can clearly see also from here that the sample is mainly characterized by the pyroxene composition, with some small dark, small grains that are olivine enriched. Some one are olivine dominated, someone has olivine plus pyroxene, and they can be separated. And even if we reduce again the spectral angle mapper, so the tolerance, the main class are, and the main mineralogical variation is maintained. So it's just the end. So what we are going to do is to integrate this data with the mineralogical and petrographic characterization that we are doing. And we want to explore a little bit more within the different classes, the variegation of some spectral parameters that will be used at the beginning, the same that Francesca Zambon was presenting yesterday for the analysis done with the MQ data. So we can then try to make some consideration and interpretation combining remotely sensed data of the moon and meteorite spectral analysis in the visible to near infrared. So that's all. Thanks for everything.